Professor Vidyasagar, and this is a theme which I started getting interested in after the lockdown started with nothing much to do on phone. Uh, and while this whole theme started with statistics and probability, but soon the most of the interest in this has come from engineering groups, and it was Vidyasagar who introduced me into. He was teaching something and he has doubts on probability, so he asked me, and that is where this whole thing began. And then, of course, when I'm reading something in probability, I bring in B.V. Rao. So uh, the theme started around 1950. Uh, Robinson Monroe, and this was a PhD thesis by Monroe, and it's called stochastic approximation. And thereafter, Kiefer Wolfowitz introduced a similar theme and the so-called stochastic gradient method. And one can check the content and references in the books by Kushner, by Metivier, by our own friend who visits here, Borkar, who are experts in this. And the impact, these references will tell us the impact this theme has had. A lot more engineers and writing on these papers, books, chapters, etc., than probably, especially in the last 3 decades. So, yeah. So let me introduce the problem not in the statistical way it occurred, but something which we can relate to, most of us can relate to. You are given an increasing continuously differentiable function, derivative bounded away from 0 and bounded away from infinity. Newton-Raphson method gives you a sequential approximation to the 0 of the function. Okay? Classical, we learn it at the very beginning of calculus. Now, suppose that given x, we can compute gx but not g dash x. So we are not having a formula. Let's say you have a black box, you put in x, it tells you what is gx, not g dash x. Okay? But since g dash is bounded away from 0 and bounded away from infinity, we can very easily check. I'm not going to read the proof, but a very simple proof that we can still do a successive approximation. It will be weaker than the first one, but I mean, it will take longer to converge, but it will converge. Now I am changing things again. I am not computing, but observing now. Instead of given a black box, you have something which you are measuring, you are observing, and all observations, or most observations, are subject to errors. So you can observe gx, but in presence of some noise, or what statistics probablists call error. So we observe, you give me x, we can observe gx plus z. Now, if xn is our guess of, or the estimate of x star, and we xn minus 1 it should have been, and we are observing xn minus 1 plus zn, one can do a simple thing that if we apply the earlier algorithm, just our observed with a noise term in place of just g, this thing will not converge to 0. The variances will blow up. If the Zn's are, say, second moment finite, then we can easily see that variances will blow up, and therefore the approximation algorithm will not work. What do we do? Well, the answer comes in something which Robinson Monroe had done in a statistical context, is by taking a sequence beta n, step size, and summation beta n infinity, but summation beta n square finite. Okay? And this has become so common that these are called Robbins-Monroe conditions. And then if you, instead of 1 by C2, you make it 1 by, you have beta n there. So you don't update your thing with at the same rate, you bring down the rate of updation. And bring down so that the error focus goes down, but fast, not very fast, so that you converge well ahead. And this goes back to the 1951 or 50 paper, 51 paper, but 50 work perhaps, that even with this, the sequence xn will converge to the required result. Yeah. So after some point, our beta n will override the C2, and instead of C2, you do one beta n. Okay, and this also works if forget now differentiability, etc., but you have a contraction, and contraction we all know the standard method. But each time, once again, the same trick that you are unable to observe it, but you can see it only in presence of noise. Do the same thing, and it works. So the literature in stochastic approximation, depending on what they were applying for, it went on and off and on between zeros of a convex set and contraction. Theme is called stochastic gradient method, and this was soon after Kiefer-Wolfowitz had observed this soon after the Robbins-Monroe paper, that now the G that I was talking is actually a derivative of a convex function, and you want zeros of that convex function, and you cannot observe Gx, you can only observe Fx in presence of a noise. So you do a gradient, approximate the gradient, Fx plus C minus Fx minus C, and take 1 over 2C. And I've deliberately put these two in different colors. So this is the term with plus Cn, and this is the same term minus Cn, you subtract the two. Each comes with its own noise. And you have to divide, since you are increasing and decreasing Cn, you do 1 by 2n. And once again, Kiefer-Wolfowitz, 53 or something like that, they showed that this will also converge. You needed a lot more conditions on beta n, Cn, and so on and so forth. And they had not called it stochastic gradient method. This is later applications in engineering that they, I think, have given the name stochastic gradient method. Now, the original papers considered only convergence in probability. And this was extended to convergence almost surely, like the strong law of large numbers from weak law of large numbers. And while mathematically it may seem a very weak extension, in practice what is, you are observing something. If you are told that large number of people observe, on the whole most of you will be fine, that means it leaves the possibility that one time you are close, next time you may be far away. Whereas almost sure says that most of the time you will reach there and will stay near there. So that is a subtle difference between these two, not just definitional and mathematical, but a subtle difference. And works with convex optimization and works with contraction. Oh yeah, in between. Right away it was extended to D dimension. So we started with 1 dimension, it was extended to D dimension, and this was very popular. The Berkeley Symposium in the 1950s, several themes were followed in statistics probability, and a lot of people wrote about this in the Berkeley Symposium, whole lot of bigwigs. Then that was also the time when Martingale had made an entry in probability theory in a big way, and it was like a Martingale factory, that anything which you have done with independent thing, you can say that, oh, basically the same thing will work if you have a Martingale. Okay, so the extended from IID to mean 0 finite variance IID to independent mean 0 and bounded variance, and from there to Martingale difference. So all this was 50s and up to mid 60s, even late 60s. Okay, whole lot of each time you were to tweak a condition a little bit more, less, etc., etc. Now, later over the last few decades, it has found applications in machine learning, and in that the Martingale plays an important role because, yeah. In the yeah, so what is done, especially finite dimensional multi-dimension case, that you do first 1 dimension, then second, then third sequentially, or each time you pick a dimension at random and then move. And both these things work. Depending on various conditions, you can then analyze the convergence rates. Okay? And a simplest example why martingale is important than IID errors. Uh, a problem which has nothing to do with probability. Okay, let's say this is very loose description. Let's say you have a Rubik's cube, and you want to get to you know what is the end point. Let's assume that at every point you have multiple paths available, one at one step, and let's say you can make out some paths to be avoided. So you know that on the average you are going to go towards the right path. And at each time you pick one of the possible paths at random. Okay. But you pretend as if you have moved on the average mode because all of them are better. Okay. So if you can prove that if at each stage you will have on the average a better path, you will reach there and this one will give you. And what you treat is the difference between whatever you have chosen and the average as the error. There is no error, but error is in our mind, observer's mind, and that thing works. Okay? So this was just a simple example of a problem like our convocation day Jaykumar talked. Problem has nothing to do with probability statistics. You bring that in to prove. So it is something like that. Okay. All right. So just do a Google search with stochastic approximation or stochastic gradient descent method, and you will see the whole lot of recent articles, books, algorithms, explanations, software codes being written for that. For our CS friends here is a paper about formalization of stochastic approximation theorem. Okay? And you see the author, the first one is a PhD student, the other three are from IBM research. And it appeared, it was presented in a conference at Dax Tool. I don't know if I'm pronouncing it correctly, but yeah, the CS guys know what I'm talking about. And after PhD, he has gone on to become an engineer at Intel Corporation. So this is just to say that how important this whole theme seems to be in the present context. Okay. So briefly, I will talk about what is our, in this paper that we have done. And so we are looking for conditions on step size beta n and the noise sequence Zn so that the Xn described here converges to the unique solution X star. Okay. Standard approach is the following. You look at this whole equation and try to stochastically get distance functions and various things between Xn. Study behavior of Xn. Okay? And you put suitable conditions on beta n, G, and Zn, and so on and so forth, and you will prove convergence. So then different papers will move in different directions. There were two tools which were developed. One is martingale tools, and the other was embedding in differential equation. Being a probabilist, I am always like the martingale proofs, and Borkar, being an engineer, likes the embedding differential equation method. He has a book on that theme, and we have debated in the past a little bit, not much, because he is the expert. I used to be an outsider. He used to be. Now, both these have some advantages and disadvantages. Probability theory or martingale tools don't start unless you have the square integrability condition. And whereas differential equation thing, they could do without it. So that was one big thing up their thing, all right, up their sleeve. All right. So the Robbins-Monroe conditions, I mean, 1 over n satisfies it, but you want to improve the rate of convergence, you can do some other tricks, and you can take n power minus gamma, where gamma is between half and 1, strictly above half. Now, the main contribution of our recent paper, recent is like acceptance was like a week ago, okay? And the work has been in last 1 year, submitted and everything processed now, is what I am calling transfer principle. So let's fix for now a step size beta n satisfying Robbins-Monroe condition and the noise sequence Zn. Okay, we'll say that Zn is satisfying generalized strong law of large numbers if, now this expression looks weird, but we are as if that function g is not there. Okay, and I'm gx equal to x, and I'm writing down the old equation. Gx equal to tx, and I'm written down the old equation. One thing which has come in is this multiplier, which for now we can ignore. I will explain why this multiplier has been put. But when the multiplier is 1 and beta n is 1 over n plus 1, we'll see that what I'm claiming happen and t equal to 1. What is I'm claiming is the law of large numbers. So Kolmogorov, so this will be Sn plus 1 will be x1 plus x2 plus xn plus 1 divided by n plus 1. So that will be Kolmogorov's law of large numbers. And that's why the term generalized law of large numbers that we have coined. So some extension of law of large numbers, but a little bit only. If this works, the transfer principle, what is in our paper, we have not called it transfer principle. This is just I've coined the phrase for this talk for now. We'll see. So if the noise sequence satisfies this generalized strong law of large numbers, and the function g satisfies this condition, where this condition will be satisfied by both our examples that we looked at, that g dash between bounded or the second derivative of a convex function, etc., satisfying and contraction principle, contraction function, all these will satisfy. Then once again the approximation works. Okay? And here the multiplier is important, because when you are observing the error term, the variance of the error term could be allowed to grow when depending on what you have observed or where you have moved there. So in a linear sense. So here the multiplier is allowed based on the history, but it cannot be more than a linear rate. Even then the approximation works. And which one? No, not a linear. No, just it can be arbitrary function. It doesn't grow more than linear. That's it. It doesn't grow more than linear. That is the important part. And that is what is missing in some papers. It will be only a linear function of the last one, but not the entire history, and so on and so forth, depending on the proof techniques used. Nothing. For the generalized law of large numbers, we had that Zns are arbitrary functions but bounded, uniformly bounded. And that gets translated in transfer principle to linear. And the main thing is that you have one set of conditions on the step size and Zn, and another one on the function g. These two are kept decoupled. Okay? Whereas the standard analysis, the two get coupled, because you are looking at L2 analysis on the Xn itself. Then somewhere or the other g and the second moments of Z come into the picture. Okay. Gx is 0. That's it. Yeah. So if Gx is 0, then of course we'll, yeah. So it is, okay. And the interesting thing is that the proof of this principle is only an L1 proof. So as yet we are still working, but typically probability theory on Banach spaces, it brings in geometry, because you want to use the any probabilistic thing in Banach space, you need some geometry condition. Goes back. So here it will be saying that if for somehow by some method you can show that your error terms are controlled well, then the function g, no geometry comes into the function, this part. This is a, L1 means no geometric condition. L2 means you need some geometric condition. So that is the big part of this. This is, the Banach space version is still little bit to be fine-tuned. It is there but not there. Yeah. And the same thing, transfer principle also works for stochastic gradient descent. Typo SGD, it has come SDG, but so we have a same condition, but the gradient, approximate gradient satisfying this condition, and rest of the thing is the same. We still have that if the error sequence satisfies generalized strong law of large numbers, so does and here the role of this function, the rate of Cn and this eta n comes in very clearly. It only is eta n divided by Cn. Whereas in the standard analysis, going back to Kiefer-Wolfowitz and all papers, the conditions are on eta n divided by Cn as square as well as eta n times Cn. One term there is the product and one term there is the ratio. It comes into the picture, whereas here it doesn't. So the main advantage, as I see it, is that decoupling the connect between the error terms and the whatever G function we are trying to approximate, whatever tool we are using to prove convergence in the presence of error. Okay, and brings back the martingale tools back to square one, because this part we don't need any more geometry. So like Kolmogorov's law of large numbers, one can prove, Kolmogorov proved it, that it works even with the only L1 condition. So one can do stochastic approximation using martingale tools using only L1 condition. So that's again, indeed, maybe that is my last slide. Indeed, we have shown in our recent paper, this is the RD version, not infinite dimensional version, that the things works even if the first moment is infinite. You need slightly weak, some condition which is only slightly weaker than L1, but still, that is even L1 is not a necessary condition. It can still work without L1. And this is, so the interesting thing is that when I started as a PhD student, it was all pure theory. Okay? I was attracted to research and to this because B.V. Rao taught us probability in my probability theory 2 courses in my final year, and the when I approached him that I want to do PhD with him, the ISI system had been, and I suppose still is, that you don't pick a area and advisor on day one. You do coursework for a year and then only you figure out. So he said, yeah, but not so fast. You do the coursework. I said that I had the Science Talent Fellowship which required a signature by advisor. So B.V. Rao said that, well, it's okay. As long as it is only for the signature, I will sign. But we will see later. But I meant it seriously, and so did he. So but it was all theory. Okay, and he started studying all exotic stuff in probability and so on and so forth for years. But as it looks like on hindsight, I had this streak of looking at applied problems. But it is, others may not recognize it, but I can, that it is there with B.V. Rao also, because let's say even in my PhD years, we are studying something, I am reading a paper, and I can tell him that, oh, actually I can prove the same thing, making this condition weaker than this. Anything of this kind, I take it to him. First thing he'll say is, do you have an example? Without an example, any such extension makes no sense. Go back, work out the example, and then come back. So this streak has been there right from, I'm talking now 45, 48 years old story. But unless there is some just generalization for generalization's sake is not much fun. And this has been there. And that continues even now. Even now, morning I'll walk into his office and say that, think we have talked about this, but I can reduce it, this. He'll again say the same thing. Where is the example? Where is an example? So it has always guided in the right direction is what I meant. And that is something which is in there. As I said at the starting point, I had asked the generations of students who have been at ISI to write their memories about B.V. Rao and so on this special day. And they have sent me. I'm going to read some of them, maybe depends. And in no particular order, the order in which they were received and what I was thinking, I have prepared this. So the first one is from someone who has been at CMI long enough, often enough, not long enough, but often enough, and Tapan Sinha. And he was in the batch of the first BStats batch that B.V. Rao taught after he returned from Berkeley in 1974 or 73, I forget. So, so this group, Tapan, now this is Tapan's writing. B.V. and I go back 51 years. He used to teach us calculus. It was a brilliant class. The things I learned there came in handy for me again and again in my graduate economics program. He went on to do economics, PhD in economics and risk and this and that. With B.V. Rao and R.V. Ramamurthy, again somebody who has spent enough time here, taught courses, who is now no more. But with B.V. Rao and R.V. Ramamurthy, we used to go swimming in the long pond behind the old StatMath building. In the retrospect, they were highlights of my BStat years. What he doesn't write is that he taught B.V. Rao how to swim properly. This is what B.V. Rao, he used to float earlier and manage it, but how to do it properly is came from Tapan. That's what B.V. has told me over the years. So thanks B.V. and happy 80th. This is Tapan. Next is a classmate of Tapan Sinha from the same batch, C.N. Rao. He has also been here, given a talk. He has gone on to be a probabilist and statistician. So happy 80th birthday, Professor B.V. Rao. You have been a true inspiration for me and my fellow BStat classmates. You pushed us to aim high while caring deeply for our growth. That's tough love at its best. Then he says, the greatest, Muhammad Ali moved like a butterfly, whereas you radiate the greatest inspiration to all of us. Today we celebrate not just this milestone birthday, but the enduring impact you have had on our lives. Wish you continued good health, happiness, and many, many more years of joy. With warm regards and respect. The third one, again a batchmate, the same batchmate, and L. Ravichandran, who comes here often enough and joins us for lunch there at our CMI. Ravichandran did not do PhD. He went into, he has now retired, but he was president of Tech Mahindra. So out and out IT man. So he writes to BVR, dear BVR, you have been a teacher, mentor and guide for me and so many people in our 73 BStat batch. Your energy levels, now at 80, are out of this world and keep all of us leading an active life. The story of you walking to Rajiv's house many times, from Nilangarai to Tiruvanmiyur, that is, and climbing Raghu's 25th floor apartment are legendary, which I used to tell my work colleagues. Even though your courses, even though your course exams were tough and given sleepless nights to many 73 batchmates, I was fortunate to do okay in your classes. Wishing you the best and many more years of active life, Ravichandran. This is from someone whom most of you may not have heard or known or met, but he was BV's colleague at ISI Calcutta, Y.R. Sharma, and overwhelmed when he saw the the mail about the today's event. All the best for the event. Our best wishes to BV for a very enjoyable birthday and wish him many fruitful, healthy and pleasant returns of the life, continuing his contributions to academics. That's what Y.R. Sharma has written. The next one is Amarnath, who occasionally comes here, not that often enough, but his cousin is our English teacher. For a minute I'm forgetting, Usha. And but Amarnath comes here often enough, and he is in US. And he has written for a group of friends. This is not just him, but a group of friends. A toast to Dr. B.V. Rao, the octogenarian equation, he says. Friends, colleagues, and former students, we are here today to celebrate a man who has always treated the number 80 not as a limit, but simply as the next term in a wonderfully complex and continuing series. When I came to B1 in 1971, he, that is B.V. Rao, had a rock star-like status amongst us, having solved an open problem for 30 years standing. About that I will tell later. For those of us who were lucky enough to learn under Dr. B.V. Rao in his earlier, shall I say, more intense decades, his reputation preceded him. His exams were harder than proving Fermat's last theorem, and getting an A from him was considered greater achievement than even a PhD degree itself. Over years, the tough taskmaster has transformed into a sage, while he still demands academic rigor. But the most remarkable thing about him is his sheer unbounded energy. At 80 years young, Dr. B.V. Rao is still teaching the next generation of students and publishing research papers that exhaust people half his age. For those of you who don't know, 2 to 3:15 he has taught a class today. And I suspect it involves three things: rigorous thinking, daily fitness, and absolute refusing to let any variable remain unknown. Dr. B.V. Rao, you are a living, breathing proof of the most complex equations, prove that most complex equations lead to most beautiful and vibrant results. We look forward to seeing your next paper and perhaps even catching you on your morning walk. Thank you for the decades of teaching and your endless curiosity, and finally learning how to smile while handing back an assignment. He doesn't write, but even when somebody has got a low score, you'll get it with B.V. Rao smiling. That's what is meant by his friends there. So that is the older generation, the classmates from that era. Now, several decades later, Sujit Ghosh, he is at NC State in US, and BStat 87 to 90, a tribute to Dr. B.V. Rao 80th birthday. It gives me immense pleasure to join in celebrating the 80th birthday of Professor Rao, a scholar, teacher, mentor of extraordinary influence. I had the privilege of learning probability theory from Professor B.V. Rao during my undergraduate years at ISI Calcutta. His teaching profoundly shaped my foundational understanding of probability, which continues to form the backbone of my statistical thinking and inferential reasoning. Professor Rao possessed the rare gift of explaining deep and difficult concepts with clarity and elegance without ever compromising on rigor. His lectures were both intellectually stimulating and inspiring, leaving a lasting imprint on how I reach both theory and practice. I remain deeply indebted for the opportunity to learn from him. On this special occasion, I extend my heartfelt wishes for his continued health and happiness. These were all ISI Connects. This one is one of the few who are had nothing to do with ISI but interacted with BV on another occasion. This is Manil Mohan. It gives me immense pleasure, immense joy to convey my heartfelt greetings on the occasion of your 80th birthday. I had the privilege of attending your lectures on probability, foundations and applications at Kerala School of Mathematics in 2010 in summer. Those lectures laid the foundation of my understanding of probability theory and played a crucial role in shaping my research career. Your clarity of thought, mathematical rigor, and passion for teaching left a lasting impression on me. I remain deeply grateful for the inspiration and insight I gained through your guidance. Manil Mohan is now teaching at IIT Roorkee in the Department of Mathematics. Works on probability related things. Next, back to again ISS student, Shubhabrata Das, BStat 8487. He is now at IIM Bangalore. Professor B.V. Rao literally carried our senior batch 1 year ahead of us at ISI, teaching them 4 to 5 courses. That was one phase of life when I was truly envious. We got to attend only one course by him. Yet, even from that single course and a few of his seminars, it was evident that he's by far the finest teacher of probability and related mathematics of our generation. Above all, his remarkable mind and soul, a true inspiration. So, as coming from his Shubhabrata writing and some of the more which come, when there was a gathering of ISS students across batches, one of the debates was always how many courses you got to did you get from B.V. Rao, and those who got many will be boasting about it, and the others will be saying, "Oh, because of you guys we didn't get him because he can teach only one or at most 2 at a time." So this has been a constant debate in various such gatherings. This is now again a colleague of B.V. Rao from ISI and someone who did operations research and other stuff, but he lives in Australia, but he occasionally comes here and stays at Hiranandani. He has a flat here. He comes to CMI also. Arthanari, Thiru Arthanari. The person who taught me how to swim in our ISI pond behind RTS building, which has now vanished. The senior colleague who appreciated my interest in art by presenting me with a copy of Escher's graphic work. A mathematician who is so humble and energetic, who radiates compassion and truthful caring. A person and well-wisher since I entered ISI campus in the late 60s. He then had settled a 40-year-old problem and was still approachable. An exemplary behavior which was rare among some of our achievers. An exemplary, I'm happy to recall many occasions meeting him at Kolkata, Chennai and other places. Wish we were able to participate in this symposium. My heartfelt greetings. This is the second reference. First one said 30 years, next one said 40 years. So let me explain. This is a story I had heard and kind of okayed by B.V. later without corrections. That B.V. Rao had done a MSc in statistics at Usmania and joined as a PhD student at ISI Calcutta. And they were assigned some themes to study and focus on. And he was told to focus on quality control, which is sampling and so on. Important, but which is the least connect with mathematics, theory per se. And it seems those days there was a tradition that C.R. Rao, whenever he catches a student, he will catch and ask, what have you been doing? Why are you wasting your time? And so on and so forth. If you are able to give an answer pleasing him, you will get stipend may increase, and if you annoy him, then you might even lose the fellowship. So one such evening walk, C.R. Rao catches B.V. and asks him, almost 1 year and you have nothing to show. What have you been doing? So Bivira said, what can I do? You didn't give me an important problem. And off the cuff, C.R. Rao throws to him a conjecture in descriptive set theory and infinite dimensional measures and so on and so forth. Nothing related to what his background. It was Ulam's conjecture. Okay? And as was the style of C.R. Rao, he'll make the statement, tell you something, and then just walk away. Okay? And it seems now the different stories, 3 weeks later, 4 weeks later, 6 weeks later, Bivira walks into C.R. Rao's office and says, I've solved the problem you gave me. C.R. Rao has forgotten the problem he has given him. So what problem? So he explains to him the problem, and C.R. Rao says, that can't be, you can't have you don't know how to solve this, you don't know anything. This is Ulam's conjecture. Do you know what you are saying? Oh, you have solved it. He said, I don't know whose conjecture it is. Here is the solution. And that was all correct. It needed to be written and then submitted and all that. But essentially, that was his PhD thesis. So that is what these people have been talking about, that he had rock star status amongst the student group already when these people came. And yet, he would be equally approachable, like we all know here now, but all along. I'm keeping track of time. So one more from a MStat, BStat MStat student, Ranjan Maitra. He starts by boasting. Professor Bivira was our class teacher for first 5 semesters. so that is his. So he taught us probability, stochastic process courses, etc. And even when I went home, I would be picking out Feller's volume 1 book and read the chapters and try to solve the problems on the themes that BV has taught us. So that was his impact. Professor Bivira was much more than our teacher. He was our preceptor, our mentor, our guide, and our inspiration. Indeed, someone who we instinctively felt we should strive to aspire to be. In the second semester, after the periodical exam, he was shocked that someone had actually forgotten the half in the exponent on the Gaussian density. When I sheepishly raised my hand, he said that he said something which I use as a great effect in my introductory classes. This fellow is in Iowa Department of Statistics. He says, I use it in my introductory class. Even if you are woken up from the middle of your sleep, you should be able to say the density of Gaussian correctly every time. I was able to make my career, I am able to make of my career owes almost entirely to Professor B.V. Rao's sage and ready advice. Professor B.V. Rao was a role model for all of us. It is with great happiness that I learned that today is his 80th birthday. I congratulate him. Some more years later, this is Anirban Datta. He now has been in finance world, and he has come and met me here. He had come on behalf of Shriram Group for a meeting here. Okay, and then he came and met, and I had forgotten that I had knew him, but and met BV also here, Anirban Datta. I have only been fortunate enough to get one course from BV Rao. It was B3 probability. I am yet to come across a better teacher than him. In the guise of probability 3, he essentially taught us convergence of probability measures and everything. More than 10 years later, I was visiting NUS Singapore, Risk Management Institute, and was asked by my collaborators to teach an impromptu mini course on this theme. And I did not need any significant preparation time, thanks to what BV had taught me years ago. I am forever indebted to Professor Rao for not only teaching the subject, but also giving directives on how to look at it from a big picture and philosophical perspective. This is Apurva Khare, classmate of Anirban Datta, the BStat 97 to 2000. Some of us know him. He's my nephew. I am writing to wish my teacher, Professor B.V. Rao, a joyous and memorable 80th birthday. Right from our first year through high school, uh, we had heard that in ISICAL that there are some exceptional teachers. And B.V. Rao's name was mentioned every time our seniors brought such lists for us. So I was very happy that in B3 actually came and taught us. He is one of those teachers who are literally who can literally paint ideas in your head just with his words. In fact, I had taken extra care to write up those lecture notes, and they remained with me for a long time, even in the US. Looking back, it was probably from B.V. Rao that I first learned the importance of conveying an idea behind the proof before actually reading the proof. A practice that I try to implement in my talks and lectures now. So let me thank B.V. Rao officially for that and wish him many more years. There are some more, but I'll skip. I'll hand them over to BV, the full thing. But Alladi Sitaram, who has been BV's colleague in ISI for years and also here, though he taught here only for a few semesters. BV, one of my closest friends, turns 80 today. First of all, let me wish him a long life filled with joy and happiness. I am sure his brilliant career in mathematics will continue for many more years to come. I first met him when I was 29 and he was 31. By then he had already made a mark as a mathematician, and he had a same modest demeanor that he has even now. Since brevity is the soul of wit, I will stop here and just add that I wish him very best of happiness to BV. So let me stop. I can, on my own, I can speak for 1 hour about my interactions with him, but I think this is enough. But maybe those of someone here would like to say something. Balaji, yeah.
42 years, the year when India won the World Cup in 1983. And I mean, for us, the equally star-like experience was BV's teaching. It was a harmonic analysis summer school in Mysore. And that 1 month was enough for all these 5 courses that you talk about and all that for us. So, I mean, it's the quality of the month, because we had him from morning to evening exclusively and he was not teaching probability theory for us. See, he was teaching algebraic topology on plates. You know, we used to eat dinner at night. So we were 3 of the brats, Rajan, myself, and Sudhir Ghorpade, and the others were all seniors. So we used to be the ones asking questions in the class, showing off. And in contrast, after BV's classes and Sundar's, we had M.G. Nadkarni and B. Ramachandran to tell what good teaching is. And BV used to explain homotopy. I mean, still on the plate after the food is done, because see the deformations of the loops is easier on a wet plate, because you can see the movements, the thing, and lifting of the curves. Everything was done, and then we used to go for walks to the hill. Chamundi Hill there, and it was, I mean, mathematics walking with us, telling us about linear algebra, various things. So it's one of the most memorable things. I think also converted me. I was convinced that mathematics is a career to be pursued, and I would take some credit for getting here to CMI. Wishing you all the very best.
Yeah, I kind of know that, because the very first time I'd come to CMI in the T Nagar office, Sheshadri of course said, you should come here. And I said, yeah, I will see. And then I don't think he had even met B.V. Rao, but he says, you know B.V. Rao? I said, yeah, of course, he was my guru. He says, go and tell him that he should come here. And each time I met him, he will first ask me to come, and the next sentence will be ask B.V. Rao to come. And he was kept saying, and I used to often think that, you know, how did he come to know about B.V. Rao? And I had got the answer that perhaps you alone or Rajan, or you and Rajan together, the 83 Mysore Summer School is what did that magic. And From whatever you may have told Sheshadri, he had made up his mind that he wants B.V. Rao here. Yeah. Okay. Student here.
So I think the only component that was missing from all the tributes is a student from here who has learned from BV. And I was in the first batch that he ever taught here. And so that is a funny, let me take 2 minutes to sort of say, again, first of all, very happy birthday to you. And I hope the Mathematical Association will continue for many more years. And our batch has been famous in CMI for many reasons, perhaps. But at that time, probability was taught in the 6th semester. And immediately after that year, I think it shifted to the first year, in the 2nd semester. But in the 6th semester, like most of the career paths are decided, people are going to go out, like I was going to go to, Paris for this CMI in a exchange program. And we were not taking academics that seriously, like, maybe only for the areas that we were interested in, but everything else was just left to hang out. And probability, again, at that time did not have the haloed status that it has now at CMI and in general in life. And so we were like, okay, there is this probability, we are counting stuff, it's an extension of permutations, combinations. Now I'm very ashamed to say this in that sense, but that's how students are. And so, BV, and of course, what happened was that time the first years were taking it with us because we were the third years, but then because it has shifted to the 2nd semester, the first years are also in the class. And so they, of course, have everything to prove because they want good grades, they want sort of, good GPA, and we are sort of, our GPA is more or less decided. So our batch was very chill about it. And then we are faced with this, taskmaster, as I think C.N. Rao or Amarnath's tribute had said. And so we did not realize this till the midterm, where, where it was in this very seminar hall. I was sitting in that chair there. And one of my friends, BV had this Einstein distribution and, all uniform distribution, Einstein distribution. And he had given a question with Einstein distribution in the question itself. And one of our friends had no idea what the distribution is, in the sense that he doesn't know the name of it. But he's confident that if he knows what the distribution is, he will solve the question. So he got up from there. I have that image in my mind right now. He came here, BV was sitting at this very table, and he said, what is the Einstein distribution? BV said, no, I'm not telling you that. And then this guy, he now works in probability, by the way, so works in probability. Atul Shekhar. And so, so that is the first time that we realized that we were dealing with this demand of academic rigor. And I myself had not really fared, I'm not telling stories only about other people. I myself did not fare very well in the midsem. And my students are here, and they hopefully they won't take lessons from that. But I was very worried for the enter because I thought maybe if I'm doing badly and here's a new teacher about whom we don't know anything, maybe his passing standard is like 60 out of 100. And it could have been. And so after the end term, I thankfully the end term was okay. Learned that, my students, that like you do under pressure, I performed okay, but still I was very worried. And so I went to meet BV, and then he was very kind about it. He looked at my paper in front of me and he said, don't worry about it. He does not remember this story, I think, but I have said this to him multiple times. But that course left a deep mark on me, despite I not being interested in probability that time. Because that intensity with which you taught the course and that demand for academic rigor and that tough image of what it takes to be a mathematician, I think that's independent of the subject that you choose, like what it takes to sort of achieve excellence. And that is something that you taught me, and I think you continue to teach me every day, like because even here, I have taken shuttles with him, and he's now asking me questions about random matrices in GP, like periodic integers. because that is the current sort of paradigm in number theory where a lot of people are studying these random matrices. And so even today at 80, he has this academic curiosity about which many of the students have spoken. And I'm very deeply impressed and continue to be inspired by you. So thank you very much.
So let us close the session, and thanks to everybody who has been here today. And best wishes to BV on behalf of all of us present here and online.